Hello and welcome to another Common Core Geometry video by eMathInstruction. My name is Kirk Weiler and today we'll be doing Unit 8, Lesson number 6 on more trig applications. This is actually the last lesson in this unit, and we're really not doing anything that's different from the last lesson, or maybe even from the lesson before that. We're simply using trigonometric ratios to find missing sides and missing acute angles in right triangles. And that's it. The key here, though, is knowing that you can use trig, knowing when to use trig, and how to use it. So let's just get a little bit more practice with this. Make sure that you've got your calculators ready to go, because we're going to be using them. All right, the keys to using trigonometry. Number one, recognize that you can use or you need to use trig. Okay, and some big red flags are right triangles, solving for missing sides or angles, and importantly, rounding. Okay? The reason that I bring this up, by the way, is that there's another thing you've used before to help you solve for missing sides of right triangles, and that's the Pythagorean theorem. And sometimes students, when they see a right triangle problem, will think, oh, I've got to use the Pythagorean theorem. And that works great when you have two known sides and you're solving for the third side. But the Pythagorean theorem won't help you at all if you're trying to solve for the angles of a right triangle. Still, first step in using trig to solve problems is knowing that you can and that you should. All right, but then you need to determine whether you're solving for a missing side or a missing angle. Let me actually get out of the way. Whether you're solving for a missing side or a missing angle in the problem, because that's going to alter somewhat the way that you do the problem. But finally, you have to be able to determine which trig ratio you need to use based on the acute angle. And that's always about looking at the angle that you either know or that you're trying to solve for, and the sides that you either know or that you're trying to solve for, and then picking either the sine, the cosine, or the tangent ratio to get the job done. Sometimes you'll even have to use more than one trig ratio in a problem to work through it, all right, and we'll see that in today's lesson. So let's get right into some problems. Here we go. Coordinate grid. Let's take a look. Exercise 1. Parallelogram ABCD has vertices at 1, 4, 9, 4, 4, -3, and -4, -3. Determine the measure of one of its larger angles to the nearest degree. Again, red flags. 1, we're looking for an angle. 2, they're asking us to round to the nearest degree. This is just a huge scream that we need to be using right triangle trig. So what I'd like you to do really quickly is pause the video, plot out this parallelogram, and then we'll get down to work. All right, well, for me, there it is. There's my parallelogram, ABCD. Now, the problem specifically asks me to find the measure of one of the larger angles. I need that angle, okay? But remember, right triangle trig only works when you have a right triangle. The beautiful thing about the coordinate plane, though, the coordinate grid, is that we can easily create right triangles. And for a moment, I'm going to just get rid of all this mess, and I'm going to actually draw this right triangle in. Okay? So this particular right triangle, the one that goes like this. All right? And in fact, I have it reproduced right there, because I can easily just use counting and go 1, 2, 3, 4, 5, right? And 1, 2, 3, 4, 5, 6, 7. There. Now, I can work in this right triangle in two different ways. I can either find the measure of this angle, angle D if you will, and then use the fact that I know that consecutive angles or adjacent angles in parallelograms are supplementary, they add up to 180 degrees, or I can use it to find this angle and then add it to 90 in order to find the angle I want. Honestly, at this point, there's no way to use right triangle trig to find the measure of angle A or to find the measure of angle C. There's no way to find it directly. We will have to do multiple steps. So I think what I'm going to do is actually use a trig ratio to find the measure of angle D and then use that supplementary relationship to actually find the measure of either angle A or angle C. They're the same, opposite angles in a parallelogram. So which trig ratio should we use to find the measure of angle D? Think about this for a moment. Well, hopefully you said tangent. right? The 7 is opposite of angle D. The 5 is adjacent to angle D. And so I would say the tangent of angle D is equal to 7 divided by 5. Now, of course, we're solving for an angle here, not a side. One of the keys to solving trig problems is know whether you're solving for the angle or a side. And we have to solve for angles always by using the inverse trig functions. So I need to do, let me erase that so it looks like a -1. I need to find the inverse tangent of 7/5. For that, I'll need my calculator. As always, make sure your calculator is in the right mode. It probably is. Mine is. It's in degree mode. Make sure the radians aren't highlighted. And now I need to find the inverse tangent of 7/5. So I hit second, tangent. There it is, inverse tangent. I enter my trig ratio, 7/5. And it looks like D is 54.46. I'll say 54.5 degrees for right now. All right, 54.5 degrees. And now the measure of angle A, right, or C, it doesn't matter, will be 180 minus D. So that's 180 minus 54.5. Let me go back over to my calculator really quick. Let's do 180 minus, might as well use the answer button on here. 180 minus that, 125.53, rounded to the nearest degree, 126. So, 126 degrees. And that's it, right? A good use of right triangle trigonometry, and we will sometimes see it in the coordinate plane, because in the coordinate plane it's easy to read off sort of horizontal and vertical distances and then use them in this sort of right triangle to figure out angles. All right, so let me step out of the way, write down anything you need to, and then let's move on to the next problem. Okay, more and more of the same. Let's go on to exercise number 2. Let's see what it asks us to do. In rhombus DEFG, the common side length is 18 inches, and the smaller interior angle has a measure of 68 degrees. What is the length of its longer diagonal to the nearest tenth? Wow, what is a rhombus doing in all of this? Well, let's take a look, okay? Now, one thing that we should remember about rhombi, can never get too much of that word, what we should remember about rhombi or rhombuses is that they have side lengths that are all equal in size. So if I'm going to draw this picture accurately, I'd like to try to draw something that looks like a parallelogram, because all rhombuses are parallelograms, but I'd like to try to make it look like the sides are the same length. And it says the common side length is 18 inches. Okay, so something like this. It also says the smaller interior angle has a measure of 68 degrees, because it is a parallelogram. All rhombuses are parallelograms. So that's 68 and that's 68. And then of course these two obtuse angles are then going to be 180 minus 68. I think that's 102, or maybe it's 112. It's 112. Anyway, whatever. We want to find the length of its longer diagonal to the nearest tenth. Well, let's draw those diagonals in really quick. There's my longer diagonal, and there's my shorter diagonal. I didn't quite make it into the vertex there, but whatever. Why would right triangle trig have anything to do with this problem? Well, it's this simple. One of the many properties of the diagonals of a rhombus is that they're perpendicular to each other. And that's important. The diagonals of a rhombus are perpendicular to each other. That's very specific to a rhombus, so I can do this. But there's something else about the diagonals of a rhombus. They also bisect those angles. So remember, we were told that this entire angle was 68 degrees. That means this must be 34 degrees. Now this is really cool, because now I have 4 identical right triangles, all right? I know their hypotenuses are 18, And I know this angle is 34. I'm going to actually take this little right triangle and bring it out here. All right, something like that. This is 18. This is 34 degrees. Okay, and I want the length of this longer diagonal. Well, this leg, or this portion of this right triangle right here, which is a leg, is half of that length because it's this right here. So I'll call it x, and then the diagonal itself, the length of the longer diagonal, will be twice that value. Take a moment now and solve for the value of x. Okay, let's go through it. Well, what do we have? We key in on the angle. The x happens to be then the adjacent side. The 18 happens to be the hypotenuse. So we can say that the cosine, right, that's my right ratio, cosine of 34 degrees is equal to the adjacent side, x, divided by the hypotenuse, 18. This is one of those ones that's very easy to solve because I just need to multiply both sides by 18 to get rid of that division by 18. So x is going to be 18 times the cosine of 34. Let's do that really quick. All right. Let's do 18 cosine 34. All right. 14.92, etc. That's half the diagonal. All right. Why don't we write it down? I'll write it down as 14.92 really quick. Dot, 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 meaning that there's some decimals I haven't written down yet. But then the actual length of that diagonal, the longer diagonal, will be 2x. And let's do it. Let's go back to our calculator. Just ask it to multiply our previous answer by 2. 29.84 rounded to the nearest integer. Not sure if that's what they asked for. Would be 20, I guess it would be 30. Or if it's to the nearest tenth, it's 29.8. Let's keep both of those in our head. What do we want? What is the length of the longest diagonal to the nearest tenth? And that was 29.8. All right. So this is cool, and it's not surprising. Okay, back when we were working with rhombuses, back in the quadrilateral unit, we did a little bit of Pythagorean theorem with them. Now we can do trig, but there were two important facts of rhombuses that we needed to use in this problem. The first and most important of them all was the fact that the diagonals of a rhombus are perpendicular to each other, carving the rhombus up into 1, 2, 3, 4 identical right triangles. And the other piece, which was also quite large, was the fact that this 68-degree angle then gets bisected by the diagonals. Well, not here, that's not 68 degrees, but that 68 got cut into two 34-degree angles. That allows us to extract one of those right triangles and solve for either one of the diagonal lengths, or at least half the diagonal length, and then double it to get our full diagonal. All right, let me give you a second to write any of this down, and then we'll move on to the next problem. Okay, let's do it. Next problem. This is a cool one. And it's actually quite important, especially when we get into the last unit and we're looking at formulas like the circumference of a circle or the area of a circle. Believe it or not, this problem is going to come back to us. So let's take a look at this regular pentagon. Regular pentagon ABCDE is shown below with point F at its center. In other words, point F is located such that AF is equal to BF is equal to CF is equal to DF is equal to EF. If AF is 4 inches as shown, then determine if the pentagon's perimeter is more or less than 2 feet. All right, so I have a very easy mandate. You know, it's not going to be an easy calculation, but it's an easy thing to understand. I need to figure out that if I added up the lengths, the 5 lengths that surround this regular pentagon, 1, 2, 3, 4, 5, will it be greater than or less than 2 feet? Based on the fact that this thing, and this, and this, and this, and this, are all 4 inches. Now watch out, you might say to yourself, Well, these are equilateral triangles, so if that's 4, that's 4. So then I can just do 4 times 5, get 20, and blah. These aren't equilateral triangles, but they are isosceles triangles, right? So what I can do is I can take this thing and I can slice it like this so that I get a right triangle. Now maybe that's enough for you to get through the rest of the problem. Maybe not. Pause the video now and see if you can figure out what the perimeter of this regular pentagon is and whether or not it's larger or smaller than 2 feet. All right, well, there's a lot more work to be done. Obviously, what we really need to do is we need to figure out the length of one of these sides. And if we're going to use right triangle trig to do it, I need to get an angle, some kind of an angle, preferably an angle in this right triangle that I just drew. Okay, so how do I do that? Well, one thing that I know is that this entire angle, right, is 360 degrees. That makes sense. So one of these angles, right, will be 360 degrees divided by 5. Divided by 5, there it is. So each one of these angles is 72 degrees. 72, 72, 72, etc. That's not really the angle I want. What I really want is this small angle in here, but that's half of the 72. And of course 72 divided by 2, if you didn't already know, was 36. So that's a 36-degree angle, and that's a 36-degree angle. Why is that all important? Because now I can extract this little right triangle over here, and I'm going to draw it in a way that I feel more comfortable with. All right, something like this. I love the electronic pen sometimes. We have this 36 degrees. This is that 4 inches. And now what I can do is I can find this length from A to that midpoint there, this length. I'll call it X. All right, and I'll put it right there. Now it's pretty easy to solve for X, right? I can say, all right, I got the 36 degrees, X is opposite of it. The 4 inches is the hypotenuse. Opposite hypotenuse tells me I should use the sine ratio. I'll say the sine of 36 degrees is equal to X divided by 4. One of the simpler trig ratio equations to solve. Multiply both sides by 4. X will be equal to 4 times the sine of 36 degrees. All right, real quick, let's see about what that is. All right, go here, clear 4 sine 36, enter 2.35114, etc. I'm gonna write down 2.35 really quick. So that's 2.35 dot 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 whatever. All right. Anyway, so we've got 2.35 as the length of X, but I need the length all the way around this pentagon. So what should I do with that 2.35 to get the right perimeter of my regular pentagon? It seems like maybe I should multiply it by 5, but that's not quite right, right? To get a side length of the pentagon, I would actually take that 2.35 and I'd multiply it by 2. But then I would take that answer and multiply it by 5. So effectively, what I really have all the way around this pentagon is not 5 of these x's, but 10 of them. Do you see that? Because I'd have an x plus x plus x plus x plus x plus x, etc. So in fact, the perimeter, I don't need to do that. Perimeter is going to be 10 times that. So let's go back here and let's just ask it to multiply by 10. And the perimeter is going to be, check this out, 23.5 inches. All right? So the perimeter is going to be 23.5 inches. So what was the question asking me? Is the perimeter more or less than 2 feet? Well, 2 feet, right? 12 inches per foot. 2 feet is 24 inches. So this is just barely less. Quite frankly, of course, rounded to the nearest inch, it is exactly 2 feet, but the answer is it's less than 2 feet. And it's kind of cool. You can find the perimeter of any regular polygon, whether that is 5 sides, 10 sides, 20 sides, or anything else, by using this exact technique, right? Carving it into right triangles like this, and then solving for sort of half of one of the side lengths. And that's it. All right, let me step out of the way again so that you can write down anything you need to. Okay, let's move on. This is an important problem. We'll come back to it in future units. Okay, here we go. Let's take a look at somebody who's trying to figure out the height of a tower. All right, exercise number 4. A tower is located 327 feet from a building in the figure shown below. A person from the second story measures an angle of elevation to the top of the tower is 32 degrees, and an angle of depression to the bottom of the tower is 18 degrees. Find the height of the tower to the nearest tenth of a foot. That seems a little bit extreme, but we'll do it anyway. So I need to figure out this height. All right, and as you probably can already tell, we're going to need more than one trig ratio because we have more than one right triangle. In fact, let me make the width here a little bit larger and go with red. We've got these two triangles. We've got this right triangle, and we've got this right triangle. Well, that one wasn't drawn very well, but here, let me get rid of this last little piece. Maybe down like this. All right, so we've got these two right triangles, one up here, one down there. Okay, and let's actually draw those two triangles separately. Right, the one that's on the top, so to speak, is this one. And what do we know about that? We know that this is 32 degrees, and we know that horizontal distance is 327 feet. Now, what do we want to know about this triangle? Well, I want to know the height of the overall tower, so what I'd really like to know is that length, right? The length from here up to here. Maybe I'll call that x. Now, likewise, what we also have, and I think I'll draw it in the orientation that it's on here, is we have this right triangle, right, with 327 feet here, and this angle of 18 degrees here. And just like the previous one, I need that length. And then I'll just add those two together. So I don't want to call it x, I'll call it y. All right? So see if you can figure out the height of the tower now. All right, let's work through it. It's all about finding the right trig ratio. The x is opposite the 32, and the 327 is adjacent. That's going to give me tangent. And the same thing is true here. The y is opposite, the 327 is adjacent. What I don't know about for either one of these two right triangles, I don't know about it and I don't care about it, is the hypotenuse. The hypotenuse would be that length and that length. I don't care about either one of those. So let's do it. Let's go through this one and let's set up that trig ratio that involves the tangent. And in fact, what I can say is that the tangent of 32 degrees is equal to the side opposite, x, divided by the side adjacent, 327. And again, it's a wonderfully easy trig ratio to solve. I'll just multiply both sides by 327, and I'll get x is equal to 327 times the tangent of 32 degrees. All right, and of course I could evaluate that and get some kind of a messy decimal answer, but let's go ahead and set up this one as well. In this case, same idea. I would say the tangent of 18 degrees is equal to y divided by 327. So y will be 327 times the tangent of 18 degrees. Now what I really need for the height of the tower is I need to add those two numbers together. So literally my final answer, the height of my tower is going to be x plus y, or 327 times the tangent of 32 degrees plus 327 times the tangent of 18 degrees. So let's do it. Let's just put that calculation in all at once to our calculator. 327 times tan 32, 327 times tangent of 18. All right, here we go. Clear out my calculator. 327 times the tangent of 32, real important to close those parentheses, plus 327 times the tangent of 18, right? And by doing it this way, what we do is we avoid any kind of issues with doing this and rounding, and introducing what are called rounding errors. There's no need to, right? That's good enough. And there's the height of our tower, 310.58, etc. I think it said to the nearest tenth, which would be 310.6. 310.6 feet. All right. And again, that's it. The only thing more challenging about this problem than other ones that we've done is that we had to set up two trig ratios. They were both tangent. And then we had to add those together to get our final answer. Take a look, write down anything you need to, then we'll move on to the last trig application problem. All right, let's do it. Last one. Here we go, we got a kite. All right, let's take a look at what's going on here. A person flying a kite originally lets out 232 feet of line. At this point, the person observes an angle of elevation to the kite of 48 degrees. The person then lets out additional line for a total of 258 feet. At this point, the person observes an angle of elevation of 53 degrees. If the kite rises vertically between the 2 points in time, as shown, determine to the nearest foot how much higher the kite is at point C than it is at point B. How much higher the kite is at point C than it is at point B. All right, pause the video now and try to work through this problem on your own. All right, let's go through it. Well, the first thing that we need to know is that we're really looking for that distance. We're looking for the distance between B and C. But what we really want to do is we want to find that by calculating this distance, and then just subtracting the two. And luckily, we've just got two right triangles sitting here. Let's take a look at the smaller one. Actually, I'll move this up. I need to have it down there. And what do we have there? We've got 48 degrees. We know this is 232 feet. And we're looking for that length. I'll put it right there. That almost looks like an X. Not quite. Let me make that look a little more like an X. All right. And we've got that taller right triangle, which looks like this. It's got 53 degrees here. It's got 258 feet here. And again, I want to make sure I use a different variable name. I'll call it y. All right, and that would be this length. Okay, this is the height we're at. Y is the height we're at C. X is the height we're at B. If I want to know how much taller I am at C than at B, I'm going to calculate both of those. I'm going to subtract, and I'll have my final answer. So here we go. Let's do it. What trig ratio do we need? We've got the opposite side. We've got the hypotenuse. And so we're looking at sine. And we're looking at sine for both of them. Opposite here, hypotenuse here. So I'll say the sine of 48 degrees is equal to x divided by 232. All right, simple enough again, because we've got the hypotenuse. All we have to do is multiply both sides by 232. And I'll find that x is equal to 232 times the sine of 48. Likewise over here, I would say that the sine of 53 degrees is equal to y divided by 258. Y then will be 258, times the sine of 53 degrees. And the answer I want is going to be y minus x, right? Which is going to be 258 sine of 53 minus 232 sine of 48. All right? We can put that all in our calculator at once, all at once. Let's do it in little stages. 258 sine 53, 258 sine of 53 minus, just go back, 232 sine of 48, 232 sine 48, right? This was that larger height. This was that smaller height. Their difference will tell us how much higher the kite is from here than it was from here. And it looks like it rose about 33.6 feet. Let's see what it wanted us to round to. Shown into nearest foot. We just went to the nearest foot. Let me put down 33.6 first, which ends up being 34 feet to the nearest foot. All right, again, two trig ratios, but this time, instead of adding, we subtract them. Take a few minutes now to copy anything down you need to, and then we'll wrap up the lesson. All right, let's do it. So today was our last lesson on right triangle trig. It was probably one of the shorter units of this course, but it really hinged on the idea of the similarity of right triangles that share acute angles. Due to all of that work that we put into in the similarity unit, the last one, and then the first few lessons of this unit, plus some help from our calculator, we're able to solve for missing angles and missing side lengths of right triangles, given that we have enough information. All right, that shows up in a variety of different application problems, which we saw in this lesson and the last lesson, because right triangles themselves come up so often in the real world. All right, we'll see them a little bit more here and there, but not too much more. All right, but we should always be ready to use right triangle trig when the situation warrants it. For now, I'd like to thank you for joining me for another Common Core geometry lesson by eMathInstruction. My name is Kirk Weiler. And until next time, keep thinking and keep solving problems.